Okay, so the next problem that we're going to be doing, instead of doing a practice problem out of the book, we're actually going to set up and go through problem 935, which is one of your application problems. You will be able to hand this in for points, but we're going to go through this entire process showing you how we go about determining first the reference axis to be at the centroid of the composite area. And then once we get that calculated, using that to determine the moment of inertia about the X and Y centroidal axis. Okay. So first things first, we're going to show the composite all together. And we're going to identify our simple shapes. Okay. So I am going to, and I always like to be generous with my, my illustrations here, as you know, so don't be afraid to make them nice and big, because we're going to have to, you know, put notes on them and dimensions and all that kind of stuff. So, okay, it's going to go down the middle. Shorter at the bottom. That's right. This one is not even like the other one was. This one's going to be thinner at the bottom. Something like that. And this is actually continuous. I don't know. So we know at the bottom here, this is 30 millimeters. This height is 10 millimeters. The section in between here is 55 millimeters. Okay. This section right here, between here and here, is 10 millimeters. And then thickness here is 15 millimeters. And then we have a dimension overall here of 70 millimeters. My proportions aren't so great, but we got the dimensions. Now, first thing, we have our composite shape. We know that we need to find or identify our simple shapes within this composite, right? Within this composite. So what we're going to do is I am going to identify, really similar to the last problem that we did. Okay, where my vertical on the inside here is going to be number 1. Call this one on the upper number 2, and then the lower number 3. And what we want to find is going to be our IX dash X of the centroidal axis of the entire part. Okay. And then we want to do that very same thing, Y dash Y centroidal. We want to find that. And that's of the entire composite, So we have to find the centroidal moments of inertia about each of the individual shapes. So there's going to be 3 of them, and then we'll add those in. Now, because we are not at the centroid, so right now I have my reference axis. I put it at the centroid of shape number 1 to just kind of do myself a favor at the beginning here. Okay. You could put it down at the bottom. You could put it down at the top. You could put it at the center of one of the other ones. That's totally fine. But right now, for the first part of this problem, I'm putting it at the centroid of shape number 1. Because I don't have rectangles that are evenly distributed on either side here, the centroid of the composite is not at the centroid of shape number 1. I anticipate, because there's more material on the top here, it's going to shift up a little bit. But we have to find where that shift is, because our moments of inertia have to come about the centroidal axis of the composite. So job number 1 is finding the centroid of this composite, which was the work that we did in the first part of this chapter. Okay. So as you know, that means that we have to look at each one of these shapes separately. So we're going to look at shape number 1, and we're going to show it in relationship to that X and Y axis. I'm going to call it maybe our first reference axis, if you would. Okay. So I'm going to show shape number one. This is our rectangle in the middle. And then the X and the Y axis go through its center, right through its center. Okay. So this is C1. This is our Y, this is our X. And I know I've been highlighting that. And I think that's a little helpful, but now here's my highlighter. X, Y. This is my X and my Y. I know this to be 55 millimeters. I know this to be 10 millimeters. And now what I want to do is I want to gather that information that I need to find the centroid. Okay, so I know I need the area, number one. And I know that to be base times height, which is 55 millimeters times 10 millimeters. So I know my A1 is 550 millimeters squared. Okay. Now, I also need an X and a Y for this shape, right? X1 and Y1. Now, because the centroid is going right through the reference axis, and I kind of strategically put it there, my X1 and my Y1 are both 0. There's no offset from that reference axis, which is going right through the centroid of shape number 1. Okay, now as long as I'm here, I thought, why don't we just calculate our moments of inertia about the centroidal axes, about the X and the Y, okay, of this simple shape, right? So since it's a rectangle, our IXC1 is going to be equal to base times height cubed divided by 12. So my base is going to be parallel to the x-axis. So it's going to be 10 millimeters times the height, 55 millimeters, cube that, and divide by 12. My IXC1 is going to be a big number. You should get like 138,646 millimeters to the fourth. And here's my area, my X, my Y. Just kind of informally, lightly penciling around because I'll use that for my table later on. And then I'm going to do that very same thing for the Y right away as well. My IYC1 is going to be base times height cubed divided by 12. But now my base is going to be parallel to the Y axis. So it's like laying it down on the end here, which means that my base now is going to be the 55. And my height is going to be the 10. So because the 10 is the height, it's going to get cubed this time and divide by 12. And my IYC1 should be 4,583 millimeters to the fourth. Questions so far? Okay, then shape number 2. Shape number 2 is up here. And we need to gather the very same information in regard to the reference axis. Now this one is offset in that Y direction. So I'm going to just do a new piece of paper without flipping over so I don't have to. So shape number 2, shape number 2. So I'm going to show my X and my Y axis. My X is going to be here. My Y is here. And then shape number 2 is floating above, right? Here. I know that the distance from my x-axis here, which was my reference axis, my yellow, right? I know that's going to be half of 55. What's half of 55? 27.5, exactly. So 27.5 millimeters, we're gonna put there for right now. The centroid of shape number 2, I know this to be 15 millimeters. And I know the overall distance is 70 millimeters at the top here. Okay. So let's start kind of doing what we do. So A2 is going to be base times height, which is going to be 70 millimeters. And again, if you didn't want to write this all out, I'm okay with base times height. You don't have to write it out. But just because I do it, my A2 is going to be 1050 millimeters squared. Okay. Now, those distances, we need an x2 and we need a y2, right? x2. x2 is going to be, what is the distance on either side of the reference axis that the centroid of my shape is? And it's on the y-axis, so my x2 is going to be 0 again. And then my y2 is going to be from the reference axis up to my centroid. So this is my y2, right? So my y2 is going to be 27.5 millimeters plus half of 15 millimeters, right? Half of 15, what's half of 15? 7.5. So my y2 is going to be 35. Does that sound right? Yep. Okay. Thank you. As soon as I start getting comfortable and confident, I won't get it. Okay. All right. And as long as we're here, right, we might as well do our IXC2 and our IYC2. So again, a rectangle. You're gonna remember the moment of inertia equation for a rectangle. Base times height cubed divided by 12. So my base has to be parallel to the axis I'm summing around. So X, so it's going to be the 70 millimeters. My height is going to be the 15 millimeters. And we cube the height and we divide them by 12. So my IXC2 is going to be 19,688 millimeters to the 4th. Sean, it looks like you just came in. We are doing problem 935 right now. We're kind of in the middle. So so do your best. This is one of your homework problems or your application problems. All right, and then our next one is going to be our IYC, the moment of inertia about the centroidal axis for shape number 2. Again, base times height cubed divided by 12. Now this time, because we're looking at our y-axis, our base is going to be parallel to that. So it's going to be the 15 and our height is going to be the 70. And we have to cube that 70 divided by 12. So IYC2 428 750 millimeters to the 4th. Okay, we get to do it one more time for shape number 3. I'll wait just a little bit in case anybody needs to catch up here. Okay, shape number 3. Shape number 3. We go back to our original. We're looking at this one down here. So it's going to be down below the reference axis. This centroidal, it's is gonna go right through the center, even though mine looks offset, but as you know, it's evenly distributed. So, so let's draw our X and Y axes. I'm gonna draw this up here a little bit. So that's our reference axis again. And this time, this one is down below here. So my centroid, this is going to be centroid number 3. Okay. This distance, okay, is at 27.5 millimeters. Doesn't look quite the same, but dimensions. Okay. And then we know this is 10 millimeters high and 30 millimeters wide. Okay. So our A3 is going to be the base times the height, which is going to be 30 millimeters times 10 millimeters. A3 will be 300 millimeters squared. Our X3 and our Y3. So as we extend this down, our X3 is going to be an offset from the Y-axis, and it's down the Y-axis. So our X3 is going to be 0. But our Y3 is going to be the distance down below here. Okay. I'm going to go like this. Y3 is right there. So it's going to be the 27.5 plus half of 10, which is 5. So 5 plus 25.5 is going to be 32.5. Is that right? But it has to be negative because it's down below the Y-axis. So negative 32.5 millimeters. Does that make sense to everybody? And now we have to do our, as long as we're here, like I know this isn't part of the centroid part, but will do us a favor a little bit later. We'll do the moments of inertia about the X and Y centroidal axes. And we know those equations by heart. So IXC for shape number 3, base times height cubed divided by 12. Our base is going to be parallel to the X-axis. So that's going to be our 30 millimeters. So 30 millimeters times our height, 10 millimeters cubed divided by 12. Our IXC for our shape number 3 is going to be 2,500 millimeters to the 4th. And then our IYC number 3, it's going to be base times height cubed divided by 12. My base is going to be parallel to my Y-axis. So let me look this way. Our Y is going to be parallel to the 10. So the base then will be the 10 millimeters times the 30 millimeters cubed divided by 12. And our IYC3, 22,500 millimeters to the 4th. All right, any questions? I know it's a lot to kind of write down as we go. All right, so now as we remember from our centroidal work, or our centroid work, we make a little chart, right? We make a little chart, and that chart is based on the equation to solve for the centroid, okay? So to solve for the centroid, on my next sheet here, solve for the centroid, Now, this is the centroid of the entire composite shape. So X bar is equal to the summation of the A times the X's divided by the summation of the areas. That should sound familiar because that's the part of the chapter we did last time. Okay. And then our Y bar is going to be equal to the summation of the A times the Y's divided by the total area, or the summation of the areas individually. So I wanted to write this first because then we're going to make our chart down below with the columns that we need to fill those in. Okay. So down here, we're now going to have our shape. Then we're going to have our area for each shape. Going to be millimeters squared are the units. Then we're going to have our X distance. That's going to be millimeters. We're going to have our Y distance, millimeters. Then we're going to have our A times X. And that's going to be millimeters cubed. And then we're going to have our A times our Y. And that's going to be millimeters cubed. And then bottom, we got to sum some of them. So we're going to have shape number 1, shape number 2, shape number 3, and then this is going to be our sum column. Okay. I put my units in the top row here so that I don't have to worry about putting it in the cells. So now we go back to each one of the shapes and we fill in our information. So our area number 1 was 550. Our area number 2 was 1050. And our area number 3 was 300. Now, since we have this column here, area, and we're going to be using the sum of the area, we're going to sum that up and we should get, is it 1900? 1900 millimeters squared. Then we're going to put our X's in place here. If we go back and we look, each one of our X's was 0, and for shape number 1 as well, because they fell right on the Y-axis, all of them. So these can all be 0. Now, if we go back and we look at our Y's, our Y1 was 0, so we can put that there, but we did have values for Y2 and Y3. Y2 was 35, and Y3 was a negative 32.5. Now, as we look up on top here, we don't have summations for the X's and Y's, so we don't have to worry about those. So you don't have to sum those columns, but we will sum these two. So I'll put my little cloud around there. So now we have to multiply A times X. Well, that's easy. 0, 0, 0, right? So that means the sum is going to be 0. And then we're going to do our A times our Y's. For the first one, it's 0. But now we're going to multiply A times Y here. We're going to get 36,750 millimeters cubed. And then for this last one, it's going to be 300 times negative 32.5. So this is going to be a minus 9,750. So we're going to get 27,000 for the total there. Any questions so far? Now we're going to put the values up on top, okay? So we're going to take our summation of the A times the X's. This is a 0 divided by 1900 millimeters squared. Doesn't matter because X bar is going to be 0, right? And that makes sense because all of the X centroidal dimensions all went and fell on that Y axis. And then our Y's, okay? We're now going to take the summation of the A times the Y's, the 27,000. Make sure you put millimeters cubed divided by the summation of the area, 1900 millimeters squared. So now our millimeters squared cancels out 2 of them on top, but 1 millimeter is still left, which is good because we want that for a distance. And you should get 14.21 millimeters. Okay. Now, that's the placement of my centroid. Now it's a positive value. So what it means, if I go back to my original altogether composite, it's a positive value, so it's going to move up here. And it means that right about here, okay, right about there is the X centroidal axis of this composite. And that distance from our original reference axis is 14.21 millimeters. Okay, now that was just finding our centroidal axis. So now we can do the work of our moment of inertia. Now, not to worry. This isn't as bad as we think. So what we're going to do is, it's not like we have to go back and do everything over because we've already gotten much of the information that we need to do the total moment of inertia equation. So let's write those out first so we can see where we're at. So after we calculated our centroid, we're now going to calculate our moments of inertia. So we know that what do we call it? Ix of the centroidal axis total for our whole composite shape, it's going to be equal to the summation of the IXCs, right? And we already calculated an IXC1, an IXC2, and IXC3. So we've got that done already. We just have to sum it up in a chart. Plus our summation, sorry, got to put the summation symbol for the summation of A times our D. Now it's going to be dy's go with the X because it's going to be the distance between 2 parallel X axes. So they're going to be a Y direction. Okay. Times, and I like putting parentheses around that. And then the same thing for the Y. So YYC is equal to the summation of the IYCs, or the moments of inertia about the Y centroidal axes, plus the summation of the A times the DXs squared. Okay. Now, from what we already gathered on each one of our shapes, we have a moment of inertia about the centroidal X, the centroidal Y. We kind of did it because we were there. We already have an area for each one. So the only thing that we need to add now are our D distances. And remember, these are the distances from the centroidal individual axis to now the centroidal reference axis of the entire composite that we just moved, that 14.21. Okay, so this is all that we need yet, are our DXs and our DYs. So we're going to go back to each one of our shapes. We're not going to have to redo any illustrations. We're just going to add to it. So let's go back. Again, we went up here. Now what we want to do is we want to add this X centroidal axis to each one of our shapes. So on our first shape, this shifted up right here a little bit. 14.21 millimeters, right? To our X, we're going to call that the new XC axis, okay? So now what we need here is we need a DY and a DX distance, right? On this illustration. So our DY is going to be the distance between the original centroidal axis of the shape and now the centroidal axis of our composite. And that distance is in a vertical direction. So we call that a DY1 is equal to, and what is it? It's direct. It's 14.21 millimeters, right? Do you see that? Because that's how far it moved, because we were on the centroid of that shape and it went straight up. This is our D1 distance, okay? Now our DX1, that's going to be the distance of our centroid from the centroidal axis of our composite. Still goes right through our center. Our DX1 is going to be 0. Any questions there? So now we're going to go to shape number 2. And we're going to add that distance going, here's our X. We're going to add that distance right here, okay? So we know that from here to here, this was our 14.21 millimeters, okay? So now this is our new centroidal axis or our new reference axis. So now we need to determine what is the distance from here to that centroidal axis. And that's going to be our dy2, our dy2. So our dy2 is equal to, so how do we get that? It's going to be our y2 minus 14.21. Do you see that? So y2 is 27.5 millimeters minus 14.21 millimeters. Our dy2 we need it right here. It's this one. So here's the new centroidal axis. So we need it from the one of the composite, the centroid of the composite moved up 14.21. So now our dy2 has to go up to here, to the centroid of that individual shape. So it's going to be the y2, which was 27.5, and we're going to subtract 14.21. Oh, thank you. You're right. You're right. I was looking here. It's right here, 35. Thank you, Josh. No wonder you were like, no. 35. Thank you. 35 minus 14.21. This is 35. Yeah, the 27.5 is at the bottom there. And that number would be I've lost my sheet number 2. 20.8. 20.8 millimeters. Is it 20.79? Because I have the 2-1. Let's do that. I'm just going to hold that extra decimal place. Okay. All right. And then, so we'll need this. And then our dx2, again, that centroid is right on that y-axis. So that's going to be 0. Okay. Which is nice. We like zeros in these processes. Okay. Then we have to do it one more time for shape number 3. So shape number 3, our centroidal axis went up, right? A little bit from here to here. We know this dimension is that 14.21 millimeters. So our, put this 10 on the other side. Our dy3 is going to be y3 plus 14.21, right? dy3 is going to be y3, which was 32.5 millimeters. And then we have to add to it a negative because it's coming down from there, 14.21 millimeters. So our dy3 is going to be a negative The paper disappeared on me. What do you get for dy3? A negative what? 46.71 millimeters. Okay. And our dx3, 0, right? No offset from there. Okay. Okay. So now that we have everything that we need, okay, 4, 4, 4, 4. We have our dy's and our dx's for each one of our shapes. Now we can make our chart, right? So what I'm going to do is the chart that you're going to create is going to be this. I'm going to focus in on the headings for right now. So as you go across the headings that you need, because they're going to correspond to the equations that we have here. I'm going to see if I can get both of these on here. There we go. So first is going to be your shape in your first column. Then I put the area first. The moment of inertia times the x centroidal axis times the y centroidal axis. And then the a times the dx squared, the a times the dy squared, and then the dx and the dy. I kind of added them at the end. These can go really in any order, honestly. The order isn't important. It's just that we kind of tabulate everything. And notice that each one of these is based on what's included for the equations that we need. Now, once you get and you go through, and I did fill mine in already from the previous class, the summation columns that we need to correspond to these equations up here. So it's going to be the summation of the IXC, the summation of the IYC, the summation of the A times the DX squared, and the summation of the A times the DY squared. Okay. And once we have those, then you can plug in. Okay. So what I'll do is I'm going to leave this up here so that you can go through, verify the values, make sure you get the same answers, because the answers are correct. And the important part here is that number one, you transfer them correctly from each of the individual shapes. And number two, it's easy to do to transpose or that you get the right totals. Okay. So what I'm going to do right now is I'm going to stop recording for a little bit and I'm going to let you guys kind of fill this in. Actually, I'll pause. Okay, so as we are looking at wrapping up this problem, you should have gotten the values that we see down below at the bottom of the chart. And then we would plug those into each one of the corresponding moment of inertia about the centroidal axis total for the X and for the Y, using the summation of the IXCs right here, plus the summation of the area times the DYs. So adding those two numbers together, we get 1,380,274 millimeters to the fourth. Then for the centroidal y-axis, you're going to notice that we do the very same thing, summation of the moments of inertia about the y centroidal axis, plus the a times the dx's, which was the 0. So 455,833 millimeters to the fourth. Now, as we look at this again, the comparison would be for the same cross-sectional area, the orientation where we summed our moments about the centroidal x-axis is what produced the more rigid, the less flexible, the higher moment of inertia, the more resistance to bending in this orientation as opposed to this orientation. Okay, so if you're ever wondering, like, which way should I put it, just check a moment of inertia about each one of the axes, and it'll tell you quantitatively which one is going to be which direction if you're not sure or if they're close. Okay, so any questions about that problem? Okay, so this one, as I stated earlier, this is one of your application problems. So we did it for kind of reinforcing our process, went from start to finish. And this particular problem, we had to find that centroidal axis first, and then use that to sum or to determine our moments of inertia about each one of those axes. So check, you have one of the application problems done. Okay, so I'll stop the recording now.